For generations, humanity has imagined the same moment. The day we finally discover another Earth. A distant world with oceans, clouds, and skies, quietly waiting for us to find it. A place that feels familiar. A place that feels empty. But what if that expectation is wrong? What if the most important discovery isn't finding a habitable planet, but realizing it was never unoccupied to begin with? Because something has changed. Not dramatically. Not loudly. But quietly, in the data. The James Webb Space Telescope has been studying distant worlds in a way no instrument ever could before. Not by taking pictures of continents or oceans, but by reading atmospheres. Breaking starlight into signatures. Looking for chemistry. And in that chemistry, it may have found something unexpected. The planet at the center of this story is K218b. It doesn't look like Earth. Not even close. It's larger, about 2.5 times Earth's radius. Heavier, roughly 8 times its mass. A type of world we don't even have in our own solar system. What astronomers call a sub-Neptune. So right away, this isn't the simple story people hoped for. Not a second Earth. Not a clear destination. Something stranger. And yet, it sits in a very specific place. The habitable zone. That narrow region around a star where temperatures could allow liquid water to exist. Not guaranteed. But possible. The star it orbits, K218, is smaller and cooler than our Sun. Which means the planet has to orbit closer to receive enough warmth. From a distance, it checks just enough boxes to raise a powerful question. Could something be living there? At first, the answer seemed simple. Maybe. Then the data started getting more detailed. Earlier observations had already hinted at water vapor. That alone was exciting. Water means potential chemistry. Chemistry means possibility. But when Webb looked closer, the atmosphere became more complex. Methane. Carbon dioxide. Multiple carbon-based molecules appearing together. Individually, none of these prove anything. But together, they form a pattern that scientists pay very close attention to. Because these are the building blocks of environments where life can exist. Still, nothing definitive. Nothing extraordinary. Until one signal changed the tone completely. A possible trace of a molecule called dimethyl sulfide. On Earth, this gas is strongly associated with life. Specifically, microscopic marine organisms. Phytoplankton drifting in our oceans produce it in massive amounts. It becomes part of the atmosphere. A chemical fingerprint of biology. So when even a hint of that same molecule appears on a distant world, everything shifts. Because now, the question isn't just, can this planet support life? It becomes, is something already there? Now, this is where we need to stay grounded. This is not a confirmed detection of life. Not even close. The signal is weak. Still debated. And there are non-biological ways, under certain conditions, that such molecules might form. Science doesn't jump to conclusions. It tests them. Again and again. But even with all that caution, the presence of this kind of molecule changes the conversation. Because for the first time in history, we are not just studying a habitable world. We may be studying an inhabited one. And that distinction matters more than people realize. Because for decades, the dream was simple: find another Earth. Go there someday. Explore it. Maybe even live on it. But this planet doesn't fit that story. If life exists on K218b, it almost certainly isn't complex. No cities. No civilizations. No signals waiting to be decoded. Instead, it would likely be something much older. Much simpler. Microbial life. Tiny organisms drifting through vast oceans. Living in environments completely unlike anything we experience on Earth. Because this planet is not a paradise. Its atmosphere is rich in hydrogen. Its pressure conditions may be extreme. Its oceans, if they exist, could stretch endlessly beneath thick clouds. Some scientists describe it as a Hycean world, a global ocean planet wrapped in a dense atmosphere. Not hostile. But not familiar either. And that's what makes this discovery so powerful. Because if life can exist there, then life doesn't need Earth-like perfection. At this point, the story could have gone in a simple direction. A promising planet. Interesting chemistry. Another step forward in understanding distant worlds. But that's not what happened. Because the more scientists looked at K218b, the less comfortable the explanation became. To understand why, you need to understand how this discovery was made. The James Webb Space Telescope doesn't see planets the way we see objects on Earth. It doesn't capture oceans or continents. Instead, it waits. It watches as a planet passes in front of its star. And in that brief moment, a tiny fraction of starlight filters through the planet's atmosphere. That light carries information. Different gases absorb different wavelengths. So when scientists break that light into a spectrum, they can read what's in the atmosphere. It's not a photograph. It's more like a fingerprint. And K218b's fingerprint is complicated. At first glance, the presence of methane and carbon dioxide made sense. These molecules can exist in many environments. Even lifeless ones. But together, in certain ratios, they start to raise questions. Because maintaining both gases in large amounts over time is not simple. They tend to react. To break down. To disappear. Which means something has to be replenishing them. On Earth, that something is life. But Earth is just one example. So scientists stayed cautious. Then came the possible trace of dimethyl sulfide. This is where the tone shifted. Not publicly at first. Not in headlines. But inside research teams, the conversations became more careful. More precise. Because DMS is unusual. On Earth, it is overwhelmingly produced by biology. Tiny marine organisms generated as part of their life cycle. It rises into the atmosphere. Becomes part of the planet's chemical signature. So detecting it, even weakly, on another world, is not a small thing. But here's the problem: space is messy. Molecules can sometimes appear in unexpected ways. Under extreme pressure. Under unusual temperatures. Through chemical pathways we don't fully understand yet. So the question became, is this signal real? Or is it something else, masquerading as something familiar? To answer that, scientists ran simulations. Again and again. They tested atmospheric models. Different pressures. Different temperatures. Different chemical pathways. Could a hydrogen-rich atmosphere naturally produce DMS? Under certain conditions, maybe. But not easily. Not consistently. And not in a way that fully matched the observations. At the same time, other teams asked a different question. What if the signal isn't DMS at all? Because spectral data can be tricky. Different molecules can sometimes mimic each other's signatures. Especially when the data is faint. So alternative explanations were proposed. Other sulfur compounds. Unknown chemical combinations. Even instrument noise. This is how science works. Not by jumping forward, but by pulling everything apart first. And right now, everything is still being pulled apart. But here's what makes this moment different from older discoveries. In the past, most potential life signals faded away. Better data would come in. And the mystery would disappear. This time, the mystery is holding. Not confirmed. Not proven. But not disappearing either. And that creates a strange kind of tension. Because scientists are trained to be skeptical. To doubt. To question every result. But they're also trained to follow the data. Wherever it leads. And right now, the data is pointing somewhere uncomfortable. Not to certainty. But to possibility. And possibility, in science, is powerful. Because it changes what we look for next. Instead of asking, is this planet habitable? Researchers are now asking, what kind of processes could produce what we're seeing? And that opens two very different paths. Path 1. Unknown chemistry. Maybe K218b is a strange, exotic world where gases behave in ways we don't yet understand. A place where unfamiliar physics creates familiar-looking signals. That would still be a huge discovery. It would mean our models of planetary atmospheres are incomplete. But it would stay within the boundaries of non-living systems. Path 2. Biology. Not advanced. Not intelligent. But simple, persistent life. Microorganisms interacting with their environment. Producing gases as byproducts. Altering the atmosphere over time. Just like early life did on Earth.